Okay, let's unpack this. Imagine you're training a really smart language model, right? And you start feeding it rewards that are totally useless, maybe even completely wrong information.
And somehow, it gets better, like dramatically better at solving complex math problems.
Exactly. It sounds, well, impossible. But that's the core finding, the really counterintuitive thing in the research paper we're diving into today.
Yeah, it focuses on this technique called reinforcement learning with verifiable rewards, or RLVR, specifically on the Quinn 2.5 math models.
And the numbers they report right at the start, they're kind of shocking. Using purely random rewards, just noise-boosted accuracy on a tough math benchmark, Math 500, by over 21%.
That's huge. And get this, rewarding answers known to be incorrect give a 24.6% jump.
Wild. Even just checking if the answer was in the right format, like in a specific box, that alone was over 16% better.
And these numbers, they're getting surprisingly close to the improvement from using perfect ground truth rewards, which was, around 29%.
It's uncanny. So what this really suggests, especially for these Quinn models, is that maybe RLVR isn't actually teaching them brand new math skills from scratch.
Right. It might be acting more like a spotlight or maybe an amplifier, surfacing and boosting these sophisticated reasoning strategies the model already learned during its huge pre-training phase.
And this is crucial, the strange effect isn't universal. It's not happening across the board.
No, definitely not. The same useless rewards, they generally don't work or barely work on other big model families. Think Llama 3 or Olma 2.
So the paper digs into why and points to a specific thing Quinn math does. They call it code reasoning. It seems RLVR, even with these noisy signals, is latching onto that.
So that's our mission for this deep dive.
Yeah.
Figure out how these weird rewards work on Quinn, why they seem to fail on other models, and, what does this all mean for RLVR going forward?
Welcome to this deep dive. We're taking this really interesting paper, Spurious Rewards, Rethinking Training Signals in RLVR, and we're going to break down the key findings for you.
Especially if you're in AI machine learning working with these models, this is the kind of stuff that makes you, rethink things.
Absolutely. The central question the paper tackles is, how good does the reward signal actually need to be in RLVR for something like math reasoning? Can it work even if the signal is weak or noisy or just plain wrong?
So they kick things off with a setup that looks pretty standard on the surface.
Yeah.
Section 2.1 describes it.
Right, using an algorithm called GRPO, which is pretty common for RLVR to fine-tune these Quinn 2.5 math models. They use benchmarks like Math 500 and AMC.
And the standard approach, the control group if you like, uses ground truth rewards. Simple.
Yeah.
You get a 1 if the answer's right, other if it's wrong.
That's the baseline.
Mm-hmm.
But then, as we mentioned, they got really creative, or maybe mischievous, with the rewards they substituted in. Section 2.2 lays these out.
Yeah, designing these weak and downright spurious rewards, trying to deliberately mess with the signal quality.
Okay, so first there was the majority vote reward. The model generates like 64 possible answers.
Yeah.
And it gets a reward if its main answer matches the most common one among those 64. It's sort of like self-correction based on consistency. Pseudo-labeling, basically.
And then the format reward. This one's super simple. Did the response include that boxed thing? If yes, reward. That's it.
Zero check on whether the answer inside the box was correct, just did it follow the format?
Exactly. Purely surface level.
And then it gets weirder. Random rewards. Literally a 50-50 chance of getting a reward. Pure noise, no connection to the answer quality at all.
And maybe the strangest one, incorrect rewards. They actually rewarded the model if its answer matched a known wrong answer, which they identified using a majority vote on known incorrect solutions.
So they're actively trying to steer it wrong. It feels like sabotage.
It does. But then you look at the results. Figure 1, Figure 2, showing the Quinn 2.5 math models, 70 and 1.5B parameters. And the results are just, wow.
Significant gains across all of these weird reward types, even the random and incorrect ones.
Let's put some numbers on it again for the Quinn 7B model on Math 500. Ground truth, the best, gave that plus 28.8% absolute accuracy boost.
Okay.
But majority vote, plus 24.4%. Format checking, plus 16.4%. Rewarding the incorrect label, plus 24.6%.
And the random reward, plus 21.4%. Just incredible.
Yeah, these aren't just blips. They're big improvements, and they saw similar strong trends on other benchmarks too, like AMC and even the harder AME problems. You can see that in Figure 2 and Figure 13 in the appendix.
It just flies in the face of standard RL thinking, right? You need an accurate reward to guide the learning. How can noise or actively wrong signals lead to such positive outcomes?
And that's a million-dollar question the paper tries to answer. Their first big hypothesis, looking at these Quinn math results, is that RLVR isn't really teaching the core reasoning here.
Okay, so what is it doing then?
It seems to be somehow eliciting or surfacing these powerful abilities the model already picked up during its massive pre-training phase. Section 2.3 discusses this. It's like the skills are latent, and RLVR, even with a bad signal, is somehow triggering them. More selection than instruction.
Right, selecting or amplifying what's already there. Okay, so this weirdness happens on Quinn math. Does that mean RLVR is just generally less picky about reward quality than we assumed? For all models?
That's the next logical question, and exactly what they tested in Experiment 2, looking beyond Quinn. Section 3 covers this.
So they broadened the scope.
Yep. Included general Quinn 2.5 models, not just the math ones. Also brought in Olmo 2, the base, and the instruction-tuned versions, and different Llama 3 models, 3.1 and 3.2, base and instruct. A much wider net.
And what happened there? Did the weird rewards work on Llama or Olmo?
Well, Figure 3 tells a very different story. The general Quinn model still showed some gains with the non-random spurious rewards, but often not quite as dramatic as the specialized math ones.
Okay, so still some effect on general Quinn, but the others?
Llama and Olmo. Almost nothing from the spurious rewards. Minimal improvement, sometimes even worse performance. They really only benefited significantly from the proper ground truth rewards.
Ah, so the weak signals, the random noise, the wrong answers, they just didn't move the needle for Llama and Olmo.
Exactly. This is super important. The same reward signals giving these huge baffling gains on Quinn models. They mostly just fail on models with different architectures or different pre-training data.
It really strengthens that idea that it's not about RLVR itself, but about what the model brings to the table from its pre-training.
Precisely. It points very strongly to differences in the pre-training data, the learned behaviors, the internal strategies. That's likely the root cause of why Quinn reacts this way and others don't.
And there's a practical warning here too, isn't there? The paper mentions that a lot of recent RLVR research, especially for math, has used Quinn models because, well, they're good at it.
Right. And the risk is that researchers might draw conclusions based on Quinn that just don't hold true for other models, like seeing these gains from weak rewards and thinking it's a general RLVR property.
When it might just be a Quinn-specific phenomenon, they stress the need for validation across diverse models. Figure 4 even shows similar Quinn-centric effects for other related techniques.
Absolutely. Critical point for the field. Don't assume Quinn results generalize without checking.
Okay, so if it's not universal, let's zero in on Quinn. What makes it different? What did Quinn math learn during pre-training that makes it susceptible, or maybe receptive, to these weird signals?
This leads into Section 4, where they really start investigating the mechanism. The hypothesis is clear. The different outcomes are down to different pre-existing reasoning strategies baked in during pre-training.
And they identified a key strategy, code reasoning. Specifically in the Quinn 2.5 math model, section 4.1.
Yes, this is really interesting. Code reasoning here doesn't mean the model is actually running code externally.
Right, it's not like calling a Python interpreter.
No, it's the model generating Python code within its own response as part of its thought process, like using code as a kind of internal scratchpad or structured thinking tool. Figure 5 shows an example.
And crucially, they found that before any RLVR fine-tuning, the Quinn 2.5 Math 7b model was already doing this a lot, like 65% of the time on Math 500 problems.
And here's the kicker. When it used this code reasoning strategy, its accuracy was way higher, about 61% compared to when it just used natural language reasoning, where accuracy was only 35%.
Wow. Table 1 shows this starkly. So for Quinn math, using code internally was already a highly effective, frequently used strategy right out of the box.
And they contrasted this with the other models. Llama, base Olmo 2, even the smaller general Quinn model, they barely generated code. They called them no-code models.
Okay.
Then there were others like the instruction-tuned Olmo 2 and the bigger general Quinn model. They did generate code sometimes, bad code models, but for them, using code actually correlated with worse performance.
So they learned to use code, but maybe ineffectively or for the wrong kinds of problems.
Something like that. The key is that this effective accuracy-boosting internal code reasoning seemed unique to the Quinn math family in their tests.
And where might that have come from? The paper speculates maybe its pre-training data included math problems being solved using code examples.
That's a plausible idea. They also mention an interesting finding in Appendix F. Quinn math is good at handling number variations in problems, but struggles if the story or narrative changes. That kind of fits with pattern matching on structured code-like solutions it might have seen.
Okay, so the theory takes shape. Quinn Math has this effective code strategy baked in. Maybe the spurious rewards aren't teaching math, they're just pushing the model to use that code strategy more often.
Exactly the hypothesis. And they tested it in experiment 3 by tracking performance and how often the model used code reasoning during RLVR training. Section 4.2, figure 6.
And what did they find? Did the code use go up with the weird rewards?
Bingo. For Quinn 2.5 Math 7b, when trained with those spurious rewards format, incorrect, even random, the frequency of generating code shot up really fast, to over 90%. And this increase perfectly mirrored the gains in accuracy.
Wow, so the weak reward basically tells it, whatever you're doing, do more of it.
It looks that way, and the most prominent successful thing Quinn Math was doing was this code reasoning. So it doubles down on that.
They break this down even further, right? Looking at how the model strategy changed on individual problems. Figure 7, Table 2.
Yeah, they looked at accuracy changes based on whether the model stuck with language, stuck with code, switched from language to code, or code to language.
And for Quinn Math, the big gains came from
A very large portion of the improvement, like nearly 60% for the 7b model, came from problems where the model originally used language, but then switched to using code reasoning after the RLVR training, lang code.
So RLVR with spurious rewards is effectively nudging it towards its better strategy.
Seems like it. Interestingly, with the ground truth reward, code frequency also rises initially, but then as the model gets really good, the code frequency starts to decrease a bit.
Huh. What does that suggest?
Maybe that high-quality supervision eventually teaches the model to be correct without always needing that specific code crutch. Perhaps it learns more generalizable reasoning ability eventually. It's a different dynamic.
And what about those bad code models, where using code was detrimental?
The flip side holds true. For the general Quinn 2.5 7b model, where code use was bad, the RLVR gains, even with spurious rewards, came mostly from switching away from code reasoning. Code lang switching accounted for like 94% of its improvement.
So RLVR isn't blindly promoting code everywhere. It's promoting whatever strategy is most effective for that specific model's pre-training history. If code is good, more code. If code is bad, less code.
Exactly. It's amplifying the model's optimal pre-existing behavior, whatever that might be.
Okay, that's compelling correlation. But to really prove the code reasoning is causing the gains under spurious rewards on Quinn Math, they needed more direct evidence, right? Causal evidence.
Right. That's experiment 4, where they did explicit interventions. Section 4.3, trying to directly control the code reasoning.
How do they do that?
2 main ways, inducing it and inhibiting it. First, they tried forcing the models to use code.
Like just telling it to.
Pretty much.
Yeah.
Adding a simple instruction like, let's solve this using Python, to the prompt.
And the result.
On the Quinn 2.5 math models, this simple prompt significantly increased performance, like an almost 12% jump for the 7b model, shown in Table 3.
Just from asking it to use Python.
Yeah. And this reinforces the model specificity. The same prompt made Llama and Olmo models perform worse.
Because their code reasoning wasn't effective.
Right.
Okay, that makes sense.
They also tried training with a dedicated Python reward, literally just rewarding the model if the output contained the word Python. And guess what?
Boosted Quinn Math performance.
Yep. Figure 8 shows that too. Mirrors the prompting result. Inducing code helps Quinn Math.
Okay, so that's inducing it. What about stopping it? Inhibiting code reasoning.
They used compound rewards. For instance, you only get the format reward if your response does not contain Python code. Figure 9 shows this setup.
So, rewarding format following, but penalizing the code strategy.
Exactly. And on Quinn 2.5 Math 7b, when they inhibit encode this way while using the format reward, the performance gains completely vanished.
Wow. So the format reward only worked because it was implicitly triggering the code strategy. Stop the code, stop the games.
It really looks that way. Suppressing the effective strategy breaks the spurious reward effect for Quinn Math.
What about the bad code models, where code was harmful?
Here's the beautiful confirmation. For models like Olmo 27b SFT, inhibiting their bad code reasoning actually increased the performance gains they got from format or incorrect rewards.
So helping them switch away from their bad strategy made the spurious rewards work better for them.
Precisely. It all fits together. RLVR seems to amplify the effective pre-existing strategy for a given model, whether that's using code, Quinn Math, or avoiding code, some other models. This feels like really strong evidence.
Okay, this framework helps explain a lot, but let's circle back to those really baffling ones. The incorrect and random rewards. How on earth can rewarding wrong answers or just pure noise actually help?
Let's take incorrect rewards first, section 4.4.1. The paper suggests a couple of possibilities. One idea is that Even if the final answer is wrong, it might be numerically close to the right answer.
So maybe some of the intermediate steps the model took were actually correct or on the right track.
Potentially, yes. And those partially correct steps might get some accidental positive reinforcement, even if the final result fails.
Okay, that's plausible. What's the other idea?
It's similar to the format reward idea, just requiring the model to produce any kind of structured, verifiable output that looks like a final answer, even if it's wrong, might implicitly force it through a more rigorous reasoning process.
And that process might trigger the beneficial code reasoning strategy in Quinn math.
Exactly. It's less about the wrongness and more about the structural constraint of producing an answer.
Okay, I can sort of see that, but random rewards. Section 4.4.2, that still feels like magic. How does pure noise provide a useful signal?
This is the deepest puzzle. Theoretically, you're right, a 50% chance of reward, totally unrelated to the action. The expected advantage should be 0. There shouldn't be any directed gradient telling the model which way to go.
Yet we saw it gives significant gains and boosts code frequency in Quinn math. How?
The paper's explanation is really interesting and points a finger at the optimization algorithm itself, GRPO, and specifically a component called the clipping mechanism. There's a derivation in Appendix B.
Clipping, what does that do?
Clipping basically limits how much the model's policy, its strategy, can change in response to any single reward signal or advantage estimate. It's meant to stabilize training.
Okay. And how does that create a signal from noise?
The hypothesis is that this clipping introduces a subtle bias. Instead of perfectly following the theoretical 0 gradient from random rewards, the clipping makes the algorithm tend to favor reinforcing actions or strategies that are already highly probable for the model if they happen to receive a positive reward by chance.
So for Quinn math, its dominant high probability strategy is this effective code reasoning. Random reward hits sometimes.
And the clipping mechanism gives that existing strategy a little nudge, amplifying it slightly over time, even though the reward signal itself has no direction. It's exploiting the model's existing bias.
It's like the algorithm latches onto the strongest habit when it's confused by noise.
That's a good way to put it. The algorithm inadvertently amplifies the model's dominant prior code reasoning in this case because there's no other strong signal to follow.
Did they test this hypothesis about clipping being the culprit?
They did. First, Figure 10 shows random rewards with different probabilities, not just 50-50. Still caused gains and boosted code frequency, as long as the probability was greater than 0. But Figure 11 is the clincher. They ran experiments where they removed the clipping mechanism from the GRPO algorithm.
And what happened to the random reward effect?
It vanished. Completely. With random rewards but no clipping, performance just stayed flat or bounced around randomly. No systematic improvement, no increase in code frequency.
Wow. So the random reward miracle on Quinn math seems to be an artifact. Not learning from noise, but the optimizer interacting with the model's strong pre-existing strategy.
That's what the evidence strongly suggests. It's less about the reward signal and more about the interplay between the algorithm's bias and the model's prior knowledge.
Okay, let's try and wrap this up then. Summarizing the main findings from this really insightful paper, covered in Section 6. What are the big takeaways?
First and foremost, the base model matters a lot. Its pre-training history, the data it saw, the strategies it learned, these fundamentally shape how it will respond to RLVR.
Right, it's not a blank slate. Second, even seemingly useless rewards, spurious, random, incorrect, can sometimes lead to significant performance boosts.
But crucially, how they do that seems to be by triggering or amplifying useful behaviors the model already had, like that code reasoning in Quinn math. It's more about elicitation than teaching brand new skills.
And that leads directly to the third and perhaps most critical practical point. Results from one model family might not generalize.
Especially if that family, like Quinn, seems unusually receptive to these weak signals, possibly due to its specific pre-training, like this code reasoning capability.
So the big warning for researchers and practitioners: if you develop an RLVR technique and see great results on, say, Quinn,
don't stop there. You absolutely need to validate it on a diverse set of base models, Llama, Olmo, others, to see if the effect is real in general, or just a quirk of the first model you tested.
That feels like a really important piece of advice for the field moving forward.
It really does. This whole investigation kind of forces us to reconsider what we mean by a useful training signal in RL for these huge language models.
Yeah, if pure noise filtered through an optimization algorithm can amplify a pre-existing skill and give massive performance gains on some models, what does that say about the learning process?
Is RLVR in these scenarios truly teaching new fundamental reasoning abilities? Or is it acting more like a sophisticated selection mechanism, finding and promoting the best strategies the model already learned, perhaps implicitly, from trillions of tokens of pre-training data?
And if it's more about selection and amplification of prior knowledge, what does that imply for how we design future training, or how we even evaluate what these models truly understand versus what strategies they've simply learned to deploy effectively?
It definitely leaves you with some deep questions to chew on about the nature of learning and capability in LLMs.
A lot to think about indeed. Thanks for joining us for this deep dive.